This will be a video for reviewing the force practice set number 4. So find the mass of an object that accelerates 5 meters per second squared with a force of 50 newtons. So that's our F, that is our A, we're solving for M, so 50N equals 5 meters per second squared times mass. Divide both sides by 5, that's going to cancel out, that'll cancel out to 10, so our mass is going to be 10 kilograms. Find the mass of an object that accelerates upwards, which will be 10 meters per second squared. We're solving for mass. This is going to be more acceleration, and that's going to be the force. So if 50 newtons is equal to the 10 meters per second squared plus 15 times the mass, we're going to divide both sides by 25, and the mass will be 2 kilograms. Now you might be wondering, why are we adding 10 meters per second squared plus 15 meters per second squared? So if this is me, and I am holding the object, and I am then going to accelerate it upwards at 15 meters per second squared, there is a force that we haven't yet talked about that I've already countered, and a downward rate of acceleration that I've already countered. That downward force would be F of G, right, which would equal whatever the mass is times 10 meters per second squared. So if we're going to account for force due to gravity, we are talking about A of G of 10 meters per second squared. That, if I'm going to accelerate the object at 15, that means I've already accounted for this 10. Meaning I need to give the object enough force not to just hold it still in the air, but an additional force to be able to accelerate at that rate. So I must account for that, which is what I'm doing right here. Find the mass, we're solving for M, of an object that accelerates, here's our acceleration, with 10 newtons of friction, and here's our push. So if our push of 50 newtons is going to equal friction, 10 newtons, plus the force of how quickly the object will actually accelerate, we're talking about 5 meters per second squared times its mass. So why is that the equation? 50 newtons equals 10 newtons plus 5 meters per second squared times mass. Here's why. If we are thinking about the total push that I give to an object, that is going to equal the force of friction plus the force exerted on the object after we have accounted for friction, which will result in its motion. So the push is the total force that I have available to act on the object. If I want the object to move at a certain rate, I need to not only push it hard enough to move it that quickly, but I also have to overcome any friction. So I must account for friction and account for how quickly I want the object to be moving in my push, also known as net force. So this is when we are talking about horizontal motion. If we're talking about vertical motion, we use the word thrust, right, when we're talking about rockets. No different than total force, net force, or really the force of the push or whatever you've got to act on that rocket or object going upwards. That will instead be equal to force of gravity plus the force of the rocket, or frocket. So the force of the rocket, meaning how much force is being exerted on that object to get it to move at whatever rate is desired upwards, you also need to account for the force of gravity when you're determining how much force in total, your net force, your thrust, you must place on the object. So that is why here we have our push is equal to our friction plus the rate of acceleration that we want that mass to be going. This is what we're solving for. So what we're going to do is we're going to subtract friction from our push, our total force, and we're going to be left with 40 newtons equals 5 meters per second squared times the mass. Divide both sides by 5, and we get a mass of 8 kilograms. So really, as we're thinking this through, if we've got a total force of 50 newtons, right, that's the push that we put onto the object, unfortunately, we've wasted 10 of those newtons of that push on friction. Because friction is a force that slows down motion, we subtract the force of friction off of the total force of the push before we can figure out how quickly that object will accelerate. In number 4, there's a 10 kilogram mass hanging mass attached to a 20 kilogram block on a table. So always draw a picture. There's my little pulley system. Here's a block on a table attached to this block right here. This one is 10, this one is 20. How fast will the block on the table accelerate? Remember, there is no friction. Unless friction is stated, we're assuming there's no friction. So this 10 kilogram hanging mass will accelerate downwards due to gravity at 10 meters per second squared, which is a total of 100 newtons of force. If there's 100 newtons of force acting on this 20 kilogram object, 100 newtons divided by 20 kilograms, that object, the 20 kilogram block, will accelerate at 5 meters per second squared. If, for instance, in a different problem or a related problem, I said now there's 20 newtons of friction on the table, that 100 newtons, we'd have to subtract the 20 newtons of friction to get 80 newtons left over after you've dealt with friction. That is, 80 newtons applied to the 20 kilogram object would result in the block only moving 4 meters per second squared. There we see the direct relationship between friction slowing down an object's motion. There's a 25 kilogram rocket with 500 newtons of thrust. How fast will it accelerate? We're solving for A. I always suggest drawing a diagram. A diagram is a picture that has words and arrows and that kind of stuff on it. So it's a 25 kilogram rocket. There's the tip of the rocket, there's its wings, there's its fire blast against the Earth. We know that there's 500 newtons of thrust. The downward force of gravity, F of g, is going to be equal to 25 kilograms times 10 meters per second squared equals 250 newtons. So the thrust, 500 newtons, is equal to 250 newtons plus the mass of the object times its acceleration. Subtract 250 from both sides, you've got 250 newtons equals 25A. Divide both sides by 25 and you get 10 meters per second squared. Another way to solve this is to say 500 newtons of thrust divided by the mass, 25 kilograms, will give you 18 meters per second squared. Now 18 meters per second squared is how fast that rocket should accelerate if there's no gravity. But we know that there's going to be gravity because we're launching this rocket from Earth. So we subtract the 10 meters per second squared, that is the downward rate of acceleration due to gravity, and we come out with 8 meters per second squared. Oh, sorry, I did this math wrong. Haha. That should be 20 meters per second squared minus 10 equals 10 meters per second squared. I was like, hold up, that doesn't work out to the right number. Number 6, the statement can be true or false. Explain both sides. The stronger the force, the faster an object moves. I'm just going to refer down to the answer key down here. That is true if we're thinking about it from the standpoint of a push. If I push an object and I push it harder, it will go faster. Right? If I take a baseball and I throw it kind of hard and then I throw it really hard, we expect the baseball to go faster when it's thrown really hard. If the force that we're talking about here, the stronger the force, the faster an object moves. What if the force that we're talking about is the force of friction? If the force of friction is greater, is the object going to move any faster? No. The object will move more slowly. It also depends, as C states, on the terminal velocity of the object, which depends on the object's mass. So if we're talking about a ping pong ball, I can hit that ping pong ball harder and harder, but at a certain point, it's not going to accelerate anymore. It's not going to get any faster because of its tiny mass. It will have hit its terminal velocity, and air resistance, wind resistance, will keep it from accelerating further. We've all experienced this if you've ever tried to throw a feather. You can't throw a feather very quickly no matter how hard you throw it. That's because it hits its terminal velocity, because the air molecules have as much mass as the feather does when you think about the air molecules in total.